Welcome back, ladies and gentlemen. Here we are once again. We just finished dealing with distance and displacement. Now we're going to continue with speed and velocity. And really, speed, not going to be that important. We really just need velocity. Because as mentioned in a previous video, this is going to be basically an entire thing about vectors. Vectors are what we care about, and vectors are what we're going to deal with. But for a quick review, right, and remember, you have a copy of your notes. So the quick review here, as it says, is that speed is the time it takes to cover a distance. Okay, so here we go. Speed is the time it takes to cover a distance. There's no direction to this, so the answer is only stated with a magnitude. And the key thing here that we're going to be dealing with is the formula. And the formula for speed, we'll do it in red, is just V is equal to D over T. And if we do a quick example of this, as we have in the notes, we say that you have a race and cover 20 meters in 2 minutes, which isn't really a race so much as a sachet, perhaps. So 20 meters is 20 over 2 minutes. Well, 2 minutes is 60. 1 minute is 60 seconds, so this would be 120 seconds. And this will give us a total of 0.16 meters per second for a speed. Now, when it comes to meters per second, people usually have a hard time visualizing it because we don't deal with it in a lot of room and a lot of time here. So here's our fancy meter stick. 1.6, that's about to there. So from where my hands are, so about that big of a space. So I covered this much distance in 1 second. So that means I went about that fast. So realistically, it's not a race so much as me walking at a reasonable leisurely pace all the way to the end. Converting is something that we're going to need to do here and there, and there's a few different ways to convert. When it comes to doing this one, and this is 120 seconds, I did it very quickly because I knew that 1 is 60 and 2 would be 120. But there's another way to convert that I want to show you guys, and I may as well show it to you now. The conversion technique that I use tends to revolve around have, want, need, have, want, lose, gain. It's an algebraic way of solving this, basically the same as what you would have learned in math class, but it works for pretty much everything. So in this case, I had 2 minutes, and I wanted it in seconds, but I didn't know what the answer was. So I put it in brackets. I want to lose minutes, so minutes go on the bottom. And I want to gain seconds, so they go on the top. Now, 1 minute is 60 seconds. Now I just do the math. 2 times 60 divided by 1 equals 120, and there is our answer. It's a pretty straightforward way in which to prepare information to convert from one to another. But again, realistically, speed is pretty straightforward, I hope. We're not really going to focus on it. Instead, we're going to talk about velocity. So let's erase the board here, and we're going to take a look at a velocity question. And this velocity question is going to be in multiple parts. So this particular video is going to be dealing with a lot of different details. But each one of these is going to be of varying difficulties and complexity. I actually use a version of this question in my grade 10 classes. The difference is that you guys in grade 11 are going to be dealing with an awful lot more stuff. So as it says here, velocity is the time it takes to cover a displacement. That's the big difference, which means that velocity is not d over t. Velocity is delta d over delta t. It's the amount of time it takes for you to cover displacement. Now remember, we talked about it in the last video. Displacement is traveling in a particular direction from start to end in a straight line. So it continues on in the notes saying that though it looks the same as speed, it's actually quite different. So consider the speed you would need to make a straight trip in the same time. So we're going to explore that now. In your notes, we actually have this particular problem. Not just your notes that I've given you, but also your notebook. It's on page 10, where a lot of this stuff is reviewed. Some of the earlier stuff I've managed to type up and put in the notebook itself. Not everything. Not yet. Give it time. Now, what we see on page 10 is a rough explanation, and it tells us that there's a city block laid out in a grid running north-south and east-west. The blocks are 135 meters east-west and 45 meters north-south. Okay, so very quickly, we're going to draw one of these blocks in here. So I'll just erase this. I know I just wrote it, but you hopefully have it in your notes. So I take out a nice ruler here, and I'm going to make a block, and it's going to go like so. And let's say about to, there's a good spot. Obviously, this is just a sketch, a diagram. It's nothing fancy. We're not making anything for art class here because I can't draw, for one. You guys are going to discover over the course of these videos, I can't draw, I can't write, and I can't do math. There's a reason I teach physics. Okay, so there we go, and we're going to label this in a certain way to make sure that it matches what's in our book. So in our book, it says that this is A, this is B, this is C, and this is D. Now, what is the question going to ask us? Question 1. On your bicycle, you travel from A to B in 9 seconds. Okay, so always we want to draw what we're doing in the diagram to make sure we keep it in our minds. Some of the questions, like these ones, no. But some of the questions we're going to deal with are going to be very complicated, and we want to make sure that we don't lose ourselves. We don't lose track of what we're trying to do. So you always want to record everything you can in one place. So to that end, we'll use, say, red, and we're going to travel from A to B like so in a straight line, and it tells us that it's going to take 9 seconds in order to do that. Okay, that's cool. What else does it say? Well, that's it. It doesn't actually tell us anything more. At least, not in the question. It did tell it to us in the initial information, but I haven't written it down on the board yet. It told us that the blocks were 45 degrees north-south, or sorry, 45 meters, and 135 meters east-west. That's key, because if we didn't have the numbers, we wouldn't be able to solve this. So, the first question is, what is your average speed? So A, they're asking you, what is your speed? Which, remember, is just V equals D over T. It also asks you in B, what is your average velocity? We'll do that one in blue. Delta D, delta T. These two obviously look very similar, but they mean different things. Although, as we're going to see, not in this case. In this case, it's actually all going to work out to be exactly the same. Why? We'll talk about that in a second. So we put in our numbers. We're going to get 45 over 9. Yay. Well, that's a pretty straightforward answer, right? We're going to get, is it 5 meters per second? I think so. And would I put plus or minus? North or south? Well, I went from A to B, but, oh, right, this is a trick question. It's neither positive nor negative north nor south because it is a scalar. Scalars have no direction. You know it's a scalar because there's no arrow on top, and because it's speed, and you hopefully remember when I told you that speed is a scalar. Okay, what about displacement? Because we got to do velocity, and that needs displacement. Well, displacement is the separation from the start point of the end point, or the distance separating start-end. Well, I started here, I ended there. That's 45 meters. That's it. There's nothing fancy going on here. So this just becomes 45 over 9, 5 meters per second. So surely we must be done, right? What else could we possibly do? Velocity is a vector, so it needs a direction. There's the trick. So this, and then it's going to be south. It's not the only way we could write it. If we didn't want to write the full south, we could do meters per second s, or we could just do -5 meters per second. Now, of course, the only problem with this one is that it doesn't tell the person if it's south or if it's west. And the fact that it doesn't differentiate between those two, the fact that it doesn't tell you which one it is ambiguous. If you just tell someone, yeah, start here, go -5, they'll be like, yeah, but do I go -5 that way or -5 that way? Because both of them are negative in their respective dimensions. So this is the reason why the south comes in, because we can't be certain that -5 will be interpreted properly. It doesn't give enough information. Okay, well, that's the first question. That one was pretty easy. Let's take a look at question 2. If you travel from A to B to C to D, a lot more steps this time. All right, well, let's erase this. Get a little bit of space on here so we don't get confused. This is question 2, and it says we're going to go from A to B, B to C, C to D. Okay. Most students, when they're drawing this, immediately go from D to A as well. They end up taking it too far. Don't do that. This particular question is just A to D. Sorry, is A to B, B to C, C to D, not D to A at the end. You don't go all the way around the block, you stop early. So then the question asks, what is the distance that you travel and what is your displacement? This is where things start to get a little sneaky. The distance that you travel, we must remember that distance is found by taking the sum of all distances involved. Sigma meaning sum or add, D1, D2, D3. In this case, there's literally 3 possible Ds. D1, of course, is going to be 45. D2 is going to be 135. D3 is 45. So we take out our trusty calculator and plug them in. 45 plus 45 plus 135. 225. You'll notice I didn't actually add it in the same order that it was in there. You don't have to. The way addition works, you can do it in any order you want. And of course, it's a scalar, distance, so I don't put any direction. Doesn't matter. That's just how far I traveled. That's it. Now the second question says, what is your displacement? Well, that's where things get a little different. Last question, distance and displacement were the same. Here they're not. Because remember, displacement is the separation from the start to the end. Well, look, I started here. I ended here. It doesn't matter that I walked this long path all the way around like so. Boom, boom, boom. The only thing that matters is that I started here and I ended there. So, start to end with a straight line is like that. We start here and we go like that. So what's that separation? How big of a gap is that? Well, it's 135, because that's how big the block is in that direction. But we're not done. There has to be a direction. I just said the word direction. Well, what's the direction here? Is it south and then west and then north? No, it's just west. So I could put comma W. And that's it. That's all we have to do. This is where things are different. This is where distance and displacement are unique. And this is where it gets a little confusing for students, because they're usually like, but why? Why do we have these two things? And the reason is because if we look at this example, the orange line from A to B, B to C, C to D, that is your distance. That is like if you decide to take the scenic route, the long way. You do it the long way there. You take it slow. The dotted line is what you would do if you wanted to do it this direct route, right? Just from here to there. Boom, done. They would call this as the crow flies, is the phrase for it, because it means you just go from here straight to there. Now, by itself, this makes sense, but take a look at question 3. If the journey took 55 seconds, calculate your speed and your velocity. Well, setting those problems up is actually super simple, right? Because speed is v equals d over t. D is 225. We just measured it, divided by t, which it just said was 55 seconds. I'm going to plug that in my calculator, and I'm going to get a nice simple number. 225 divided by 55, and I get about 4 meters per second. No direction, because it's speed. Okay, that one's done. What about velocity? Velocity is just delta d over delta t. Remember our arrows? Well, that was 135 in 55 seconds. So, plug that in. But we know, just from looking at this, the setup is different. We're going to get different numbers. 2.45 meters per second. What direction is it? Because we do need direction. It is still a vector. West. Because it's still west, right? The only way for me to get from here to there, there it is, from here to there, is for me to go from here to there. I can't be like, oh, in order for me to get from A to D, I'm going to go that way. It doesn't work. The only way to get from A to D is to go west. But why are these two numbers different? Right? That one's 245.45. That one's 4. They're so different, and it makes so little sense to people when they first see this. Well, here's the thing. Remember what I was saying. The orange path on our square here is you taking the long way, whereas the green dotted line is the shortcut. What these two numbers are representing is that in order for you to arrive at D at exactly the same time, the person who's taking the long way has to run pretty fast. They have to do 4 meters a second. The person taking the shortcut can afford to go slower because they have to cover less distance in the same amount of time. What we're seeing here is that displacement is all about straight lines. Distance can wander a bit, and as a result, displacement is usually the physics way of saying this is the most efficient way to get from here to there. Okay, that's great and all, but most of this stuff so far is what I would get the grade 10s to do, right? Nothing fancy here. So where's the part that's grade 11? Why? You know what it is. You know what the challenge is going to be. We've done A to B. We've done A to B to C to D. Now we are going to do A to B to C. And what does that mean? Triangle. Triangles, triangles, triangles. So let's erase it. We'll use some different colors. So we go from A to B, B to C, which means that we have this as our displacement. Oh no. I mean, we can solve it, but as we saw in the last couple videos, anything to do with 2 dimensions is always going to be more work. That's fine, though. We'll be okay. It's just going to take some time, and we have to keep organized. That's the key. So to keep things organized, we're going to start off right down here. Down here in this area, we're going to do our scalar calculation, because the scalar calculation is not going to take a lot of time, right? It tells us also, it tells us that the journey was 50 seconds. Okay, so we're going to start off. I guess I didn't need to erase all of that now that I think about it. Oh well. Sigma d is equal to d1 plus d2. d1 is 45, d2 is 135. Plug those two together. What do we get? 135 plus 45. We get 180, says all the people who know how to do mental math really easy. And then we're going to calculate our v, which is going to be equal to d over t. So it's 180 divided by 50. This is why I had it, because this part here was going to be a little harder. We're going to get 3.6 meters per second done. Scalar calculation, very easy, almost painless, barely worth any mention. Vector calculation, going to be much harder. I mean, not really harder. It's just more work. So let's get some space here. Our calculation is still d over t. We have t, we need d. So we need to find ourselves our displacement. The displacement of anything in 2 dimensions can be found with Pythagoras. All right, so Pythagoras is a squared plus b squared equals c squared. A in this case is 45 squared plus 135 squared equals c squared. Gonna need a calculator for that one for sure. 45 squared plus 135 squared equals, square root it at the end, and you're going to get that c is equal to 142.3 meters. So that means that going from here to here directly is 142 meters. Well, on the plus side, we now know the number in order to calculate our velocity, because velocity is delta d over delta t. Okay, well, v is 142.3 over t, which we said was 50, divided by 50 equals 2.84 meters per second. Very quickly, we can compare. This is 3.6, this is 2.4, because going in a straight line is always faster than going around the block. So I don't have to go at the same, I can go slower in the velocity calculation to arrive at the same time. That's the key, is that we're making the time the same. So I can go slower. If I kept the velocities the same, right, if this one was 2.8 and this one was 2.8, then that means that in the velocity case where I'm going in a straight line, I would arrive first because I'm going at the same speed, but I have less ground to cover. Okay, so obviously we're done, and that was super painless, so what was the big deal? I mean, yeah, I write some Pythagoras in there, and I did it kind of fast, but I think you know how to do Pythagoras. You've had a lot of chance to practice it. But what are we missing? Yeah. Direction. 2.84 what? Positive? Negative? Can't do it. 2 dimensions are involved. If there's 2 dimensions, we need a north, south, east, west. To get that, we need to go back in our calculation. We need to do some trig. We need to go tan theta equals opposite over adjacent. Or if we wanted to write it another way, x over y, because 135, b to c, is horizontal, whereas a to b is vertical. Well, I guess it's this way. So this is just another way to write it, which we'll see a little later in the course, but this is totally fine. The opposite here is 135 over 45 equals tan theta. If I take 135 divided by 45, I get 3. Tan theta equals 3. Now, in order to get theta, the angle, I have to take the inverse tan. And that gives me an angle of 71.57 degrees. If you round that down, that's fine. We don't need to be that precise, to be honest. So we've got ourselves a 71.57 degrees. But now what do? We need more than just an angle. We need to know the direction that goes with that angle. Now remember, the way we talk about this is that we are comparing, right? So my initial line is going south. So I'm comparing to that. And whenever you're comparing in English, that's the thing that you say second. Why? It's just because, right? I am behind the marker. Marker's here, I am behind it. So the marker is the thing I'm comparing to. It's the second thing that I said. The south is this part going down here. The second thing that happens is me going west. So the second thing that I do is the first thing that I list. West of south. I started off going south. I'm going to instead go an extra 72, we'll say, degrees west of the south line. And that's it. That is the answer for the direction. And this calculation here is, of course, for the position. Sorry, the displacement. But here's the thing. As we already discussed when we were doing the earlier question, the only way for me to get from A to C is to travel from A to C. So the direction that I calculate here applies for the displacement and for the velocity. This direction remains the same for both of them. So once I did it once, I'm done. I don't have to do it again. I can just throw the number down in here. So I can come over here and I can say 2.84 comma 72 degrees west of south. And that's it. That is all that you need to do in order to do velocity. Obviously, the last one is a little bit more tricky than the ones before it. The ones that were all in one dimension were pretty straightforward because that's grade 10 stuff. But that's why I like to throw in a little bit of the grade 11 stuff to make sure you guys are starting to stretch those muscles, start to stretch those brains, getting ready for stuff. If you guys take a look on page 11 and 12 in your books, there is a bunch of practice problems. These are mostly very straightforward velocity problems. They shouldn't be too hard. There's some calculations, some conversions in there. You can practice that. For the most part, though, this will be hopefully a breeze. You'll see the answers on page 12. Page 13, which is our next video, is acceleration. And acceleration is usually where things get a little bit trickier, just a tiny bit. Okay, I will leave it there for now, guys. Hopefully pretty good video, and I will see you guys next time.